Blowing up? Probably all students. Yeah. All right. So again, today I'm going to talk through section 4.8. This is a one-day lesson, nice, quick, easy lesson. And then Monday, I'll give you the test review. Tuesday, you guys can work on it. And then I'd love to go over it Wednesday, and then we will test Thursday, Friday. Yeah. And then remember that we do have one more week out of the third 9 weeks past next Friday. So there's technically 2 weeks still from today is the end of the official end of the third 9 weeks. Just know that my grades will cut off at that test, the 4.5 to 4.8 test. That will be the last grade out of the third 9 weeks. For you CCP people, it doesn't really even matter because your grade all runs together continuously through the end of the year. But just know that that's where the third 9 weeks grades will end for me, and then we'll pick up. It's weird. We actually do section 4.9 at the beginning part of chapter 5 because it relates better with that. I'm guessing when they make the new version of this calculus book, when they make the next edition of it, they're gonna put 4.9 with the next chapter. But I don't write the book. Okay. This section is called Newton's method for approximating zeros. Sounds really fancy. Newton's method for approximating zeros. Honestly, I could have taught you this lesson right after we got done with derivatives. Kind of like L'Hopital's rule. It's one of those one-off lessons that it's really kind of standalone. I could have put this here. You could put it at the very beginning part of chapter 4. Just after we learn derivatives, you can do this thing called Newton's method for approximating zeros. Here's what I mean. Zeros are an extremely important piece of information when you go to graph, correct? Like that's one of the main things that you look at. One of the main things that we look at since Algebra 1. Like I teach my students how to find x and y intercepts of linear function. We find x-intercepts of quadratic functions. We find, the intercepts are an extremely useful piece of information when you go to graph the function. Well, consider this function. Consider this one right here. Let's take a look at that one. On Desmos, they start out with some really weird, wacky function like this thing. I'm not going to try to explain it using that thing. I want to use something that we will use later on. So let me hop into Desmos here. Let me jump over desmos.com/calculator. And my equation is going to be, I'm just going to write it over here so I can copy it correctly, x to the third minus 2x minus 5. Okay, x to the third minus 2x minus 5. Yep. Okay. For example, could I have found these zeros algebraically? You might be thinking, well, I could probably try to factor that, or I could use the quadratic formula. However, is that quadratic? No, it's cubic, right? The quadratic formula is on cubics. So that the quadratic formula is not going to work. I can't complete the square. That's for quadratics as well. I can't factor this thing down because, again, it's not quadratic. I would have to use some other method. Like back in pre-calculus, you probably learned that the rational root theorem, right? The rational root theorem where you had your p's and your q's, you had to find the factors of your leading coefficient and your factors of your constant at the end, and then you just like kind of threw stuff at the wall and synthetically divided and see, those are the possibilities of roots, but those were only the rational roots, right? What happens if my root is irrational? How do you figure that out? Like, for example, here. This looks like it's something just above 2, right? My root looks like it's something just above 2. But if I keep zooming in, or just, it looks like it's 2.0 there, right? But that's just an estimation, isn't it? Isn't that just an estimation? Because this is irrational. This number is going to keep if I zoom in more, that ended in a 6. Yeah, it's just rounding off there, right? 2.0946. If I go back home, interestingly enough, it's different. Why? Because that value is rounded a little differently when it's calculated. But if I zoom in a little bit more, if I go in, I bet that's enough. Yeah, it changed to the 6. Because as I zoom in, I'm getting a better approximation for what that number actually is. Here's the really cool part about this and about your calculators. Your calculators and Desmos both use Newton's method to approximate the zeros when it gives you this dot. They still use Newton's method. Now, they just do it like, calculators are really good at doing really complicated calculations really quickly. It's just really impressive how quickly that evaluates it. We're going to do that over the course of several minutes. Okay, so what is this process? Newton's method for approximating that zero. The goal for today is, again, being able to find a zero that is not algebraically possible to calculate. That's the goal for today. Being able to find an x-intercept without needing the algebra to do it. Okay. Well, let me go. I think I want to go. Oh, it's also called the Newton-Raphson method. He's another famous mathematician, Raphson. Newton came up with it first, and then Raphson kind of like made it, a little bit, like kind of incorporated a little bit better. All right. Let me show you the visual on this. Say we had this function here, right? And we know it's got a root. We know it has a 0. We know that it does cross the x-axis. We did that earlier on, right? Didn't we use the, we in the continuity section, didn't we say, well, if it's below and it's above and it's continuous in between, there must exist some root in between there? Okay, so if we know a root exists in there, what I'm going to do is I am going to pick a point somewhere along that curve, and I'm going to find a tangent line. I'm going to say, well, I've got this tangent line, and that tangent line is way easier to find that x-intercept rather than finding the x-intercept of the curve. But there's some error in there, right? It's not really exact. It's a little bit off. So why not just make this point right here, right? Why not just make that point right there? There's my tangent line. And isn't that tangent line, again, really easy to find the x-intercept? You just set it as x, 0, right? You set the y value goes to 0, and you just got to solve for the x value. But isn't that a little bit off? So what we're going to do is say, okay, well, let's make this point, the limit go to there. Let's make that point closer and closer and closer to the actual value of the root until the difference between the tangent line and the actual point at that line, or actual point on that curve, are negligible, until they look nearly identical. Until, for our purposes of rounding, you're not going to see any difference. That's what Newton's method really does. Now, how do we find that? Well, this is just point slope form of a line. Y minus y1 is equal to mx minus x1. Well, what do we know the slope is always going to change into? The derivative at that moment, right? So what we're going to do is say, well, the derivative is going to be the slope. I'm going to keep this as x1, y1, but wait a sec. I don't really care about where that point is going to go. I care about where the x-intercept of that line is going to be. So what does the y value turn into? 0. Okay, so the y value is going to turn into 0. This x1 is going to stay there. Okay, the next subsequent point is going to be x2, the next one that we plug in to get it closer and closer. Now, I'm just going to evaluate this. Watch here. This is going to be 0 minus the y value at x1 is equivalent to f prime at x1, the slope at that, times x2 minus x1, and x2 being the next subsequent point that makes it closer. Okay, get the 0 to go away. This is negative fx1, f prime x1, x2 minus x1. I am going to divide by f prime. So we have negative fx1 divided by f prime x1. So the y value at that location divided by its derivative at that location is equal to x2 minus x1. So to get the next x value, because you may be thinking, well, how do you know that next x value? Well, how do you know where that next point is going to be? Well, you can solve for it. Let's add over x1. is going to be x1 minus f of x divided by f prime x1. That is going to be your next approximation. And this process can keep happening and happening and happening and happening until you get close enough to where the difference between the actual point and its tangent is negligible. And you can say, well, due to rounding, I really don't care about how close it's going to get. That's close enough for me. I believe that's where the location of the zero is going to be. And what your calculator does is just run that value like super quick and just executes that sequence really, really, really quickly so that it does it just really fast. So that is Newton's method for approximating zeros. I would write this down. That's my formal definition for Newton's method. The next term, x sub n plus 1, the next approximation is equivalent to the x value minus the y value at that location divided by f prime at that location. Again, that is the next approximation, x sub n plus 1, is going to be equivalent to some x value that you choose minus the y value at that x value that you've chosen divided by f prime at that location that you chose. See, the thing here is that you just need a starting point. Like when I was showing you on that diagram, I said, well, let's pick some point out here, right? You picking some point out there is you choosing your x value where you want to start. And no matter how this works, no matter what x value you choose, it will always lead you toward your root. It will always lead you towards your root. Okay, whether you choose a point above it or you choose a point below it. Because I chose a point out here, right? Could I have chosen a point back here? Sure. I could have chosen that x value, gotten this tangent, find that r value, picked points, until we got to the tangent line that was actually negligible to that actual point. All right, let's practice that a little bit. Let's do that, the one that I graphed. I know it comes out to be about like 2.04 or whatever, right? But let's find that algebraically. It says find the third approximation of the root. Okay, find the third approximation of the root. They give you a starting value. Sometimes the starting value is not given to you. So how do you find that starting value? Well, you just kind of have to intuitively guess at it. You kind of like have to guesstimate at it. You got to say, well, I think it's going to be around this. I don't know for sure, but I think it's going to be around this. Then you have your starting value. Now, the worse you are at a guesser, the more times you might have to run Newton's method to get really close. If you're a bad guesser, then it might take you a little bit of time, right? You do have graphing calculators for this part, so you can go in and say, okay, it looks pretty close to 2. Let's run 2. Like if I were to go back to my graph and say, let me go back, come on, here, and I just hit the home button, I say, yeah, that's pretty close to 2, right? Let's start at 2. That's a good starting spot. I know it's pretty close. I know it's definitely between 2 and 3 on the closer end of 2. Okay. All right. So again, Newton's method is x sub n plus 1 is equivalent to, go back here, n plus 1 is equal to x sub n minus f at xn divided by f prime at xn. That's Newton's method, fxn over f prime at xn. So in this case, if I want to find x2, that means x2 is going to be equal to x1, which is 2, minus f of 2, let's write it like this for right now, divided by f prime at 2. Well, what is f of 2? Let's figure that out. So that's 2 to the third, or 8, minus 2 times 2 is 4, minus 5. Negative 1. So this is 2 minus negative 1 over. Now, what is f prime? Well, that's super easy to calculate, isn't it? That's just 3x squared minus 2. So for our purposes here, that is 3 times 2 squared minus 2. Oh, I didn't put 5. 2 squared minus 2, or 10. Right? Now, that is just going to give me the second approximation, right? That is just going to give me the second approximation. I want the third approximation. I want to go to the third. So let's calculate that. I just want to go through this just in cases. Okay, so this is 2 plus 1/10, so 2.1. So my second approximation is 2.1. So how do I get my third approximation? Well, I'm just going to do that whole process, not with 2, but 2.1. So x3, well, that's going to be x2 minus f x2 divided by f prime at that same location. Okay. So 2.1 minus, okay, let's put this in parentheses here. I've got to do 2.1 to the third minus 2 times 2.1 minus 5. That's my whole top. Divided by f prime at 2.1. So 3 times 2.1 squared minus 2. So when I hit enter, this is going to be the third approximation. 2.0946, if I round to the nearest 4 decimal places, 2.0946. And wasn't that as close as I got after I zoomed in and I zoomed in and I zoomed in? It said it ended in a 6, right? Yeah, just with 3 approximations of Newton's method, I got to correct 4 decimal places out. 4 decimal places out. That's pretty accurate, just with 3 iterations of Newton's method. Yeah, let's do this one. Use Newton's method to find the 6th root of 2, correct to 8 decimal places. You know, that was an irrational root, right? An irrational root. Other types of irrational numbers, non-perfect squares or non-perfect roots, right? This is the 6th root of a number, right? And the 6th root of 2 is just some weird decimal, another irrational number. Okay. Now, here's the issue, though. I don't have a function, right? I'm not given a function in this case. I kind of need to create that function. But I know I want its 0. Whatever function I create, I want its 0 to be that thing, right? I want it to be x equals the 6th root of 2. So you set it equal to x, and then you got to get it equal to 0, right? Because that's the root. We did this process back in Honors Algebra 2. I used to teach it. Where I gave you the root and asked you to work backward to find the quadratic, right? But this root is just weird. This root is just irrational. So to undo this thing, to get it back to equal to 0, I take the 6th power on x and then subtract the 2. So that's my function. X to the 6th minus 2. Right? You kind of got to undo everything. You got to get it back to its factor. You got to get it back to its actual equation. Oh, why did I say square? Sorry, 6. X to the 6th minus 2. Got 2 back again. Okay, so I want to find I want to find 6th root of 2, correct, to 8 decimal places. I need a starting value, right? I need some sort of starting value. I need an x1. Okay, the 6th root of 2. You know, it's got to be bigger than 1, right? Because the sixth root of 1 is 1, right? And it's got to be less than 2, correct? Because the sixth root of, well, what's 2 to the sixth power? Something really big, right? 64, is that? 8, 16, 32, 64, yeah. The sixth root of 64 is 2. So I know that it's somewhere between 1 and 2, but closer to 1, correct? So that's my estimate, my guesstimate, if you will. Let's say we start at 1. Okay, so let's find x2 in that case. Well, that would mean x2 is going to be equal to, remember that the formula, let me just write it down again. It's, let me get back here. X sub n plus 1 is equal to, x sub n minus f of x sub n divided by f prime at x sub n. Okay, now, x2 is going to be 1 minus, okay, I got to go in here. What is, looking here at f of x, what is, when I plug in 1? 1 minus 2, negative 1, divided by f prime at x sub n. Well, what is f prime? F prime of x, therefore, is going to be 6x to the 5th. The minus 2 goes away. So that's going to be, when I plug in 1 here, that's going to be 6. So that's going to be 1 plus 1/6, right? So 1 plus 1/6. 1 plus 1/6 is 1.16 repeating. Yeah, 1.16 repeating. Now, I want to get it correct to 8 decimal places, right? So I'm going to write it out with 8 decimal places. 1.1, okay, there's 1. 2, 3, 4, 5, 6, 7, and then the 8th decimal place I would round. Let's find x3. Okay, so that is 1.16 repeating. I do not want to round that number. You see how my last calculation was 1.16 repeating? I do not want to round that number in my next calculation. Here's what I mean by that. I'm going to take this and do 1.16 repeating minus f of 1.16 repeating divided by f prime at 1.16 repeating. So this is going to be actually a little tricky to put into our calculators. Here's what we're going to do. We're going to say, okay, I want to put my answer, right? Second negative sign is my answer. Answer minus, then I start parentheses, right? And I say, okay, what's my top chunk? Well, x to the 6th minus 2. So it's my answer to the 6th minus 2. Divided by my next chunk of f prime at 1.16 repeating. So 6x to the 5th. 6, and then it's answer to the 5th. You follow me there? And it's got to be plugged in using your answer button. Let's see what I get. 1 point, and now let's write it out with 8 decimal places. Okay, so that is 1 point. Okay, we got 3, 4, 5, 6, 7, 8. Right? 1, 2, 3, 4, 5, 6, 7, 8, right to there. But that'll round up. 1.1264436, and then 8. Okay, now here's where it gets a lot easier. Didn't I just run that calculation? If I plug it in correctly, didn't I just run that calculation with my answer? Watch this. If I hit second entry, isn't that going to calculate it again with just my last answer? There's x3, or x4, excuse me. So let's get this out of the way. Say so long to this guy. Oh. Get. And I want to bring over this. That is x4. Okay. And we're going to stop there, right? So 1, 2, 2, 4, 9, 7, 0, 7. Now, we're getting more accurate and more accurate, right? I want to be identical to 8 decimal places out. Right now, where am I at? Okay, so we had 1, 2. We were only 2 decimal places correct at that time, right? This is more accurate, but this one was only 2 decimal places accurate. Let's see how accurate x5 is. And again, all I need to do here, if you plug it in correctly, you just hit second entry, and there you're there. Okay. So x5, oh, that's red. x5 is 1.122462205. Okay, how close are we now? Right there. So we jumped to 4 decimal places correct. But we want to get all the way to 8. Nice thing is it's already calculating for us. Okay. Let's see where we're at now. Here's x6. 1 point. Should really get all the other one. Get up there. Get away. Okay. There's x6. 1.122462205. There it is. You see how that's identical? That way you know that all of those decimal places are accurate. Yeah. So there it is. There it is, correct to 8 decimal places out. Probably way further than we needed to go for any of our purposes of real life application, right? You know, probably we would really realistically only need to stop at like 4 decimal places out. That would probably be accurate enough for anything that we would be doing. But if you really wanted to get accurate, you could go all the way to, you know, whatever your calculator is going to show you, right? Your calculator is only accurate to 8 or 9 decimal places out, depending on what you start with in this case. Okay. Let's do this one, and then this will be our last one. Yeah. Oh, it is. Find correct to 6 decimal places the root of the equation cosine x is equal to x. Cosine x is equal to x. So what is this doing? This is taking cosine, just to kind of visualize it for you. This is saying I've got my cosine curve, and I've got y equals x. Find this green point. Find the x value at that green point correct to 6 decimal places out. Okay, so what is the equation that has that root? Well, cosine x is equal to x. I need to set that equal to 0. So let's just subtract the x over. Cosine x minus x is equal to 0. So f of x is cosine x minus x. While we're at it, let's find f prime. F prime of x, well, what is the derivative of cosine? Negative sine. And then minus 1. Okay, now, what you actually can do to kind of start this process is think about this. You know your next one is going to be x sub n minus, now what is f of x in this case? Cosine x minus x. What is f prime? Negative sine x minus 1. See, now this gives you an equation for your next one. So you don't really have to do the f prime of if you want to just go ahead and plug it in. All right, so we need to do some estimating here. Okay, we need to do some estimating here. Let's get close to this thing. It's somewhere between. What is this value here? What is that value? Where does it cross the axis there? Pi over 2, right? Pi over 2. Okay. 1.57. So it's something less than 1, correct? Or sorry, something less than 1.5. It's something less than 1.5 and something bigger than 0, correct? So starting value 1. Sound good to you guys? So you just kind of have to estimate where you think it might be. You don't care if it's an overestimate or underestimate. You don't care. It'll lead you to your root no matter whether it's an overestimate or underestimate. Right? These ones, the two that we've already done, were underestimates, right? I started at 1 and it started to increase. I started at 2 and it increased. This one, spoiler alert, is actually going to decrease us. Let's see what, let's say x1 is 1. Okay, so that means x2 is going to be 1 minus cosine 1 minus 1 over negative sine 1 minus 1. Now, I'm going to be very particular about how I plug this in, right? Once you get it plugged in your calculator correctly, you're not going to have to do it again. Okay, so I've got 1 minus, okay, I'm going to take my whole top chunk in parentheses. Cosine of 1 minus 1 divided by my whole bottom chunk in parentheses. Negative sine 1 minus 1. Right? Everybody follow me there? Just double check me plugging it in. 1 minus, whole top, cosine 1 minus 1, divided by negative sine 1 minus 1. It decreased, didn't it? I started at 1 and now I have 0.750367, 6 decimal places. Let's bring it over here. So x2 is, okay, 0.1, 2, 3, 4, 5. It's hard to count and write numbers at the same time. 750364. You follow me there? Okay, now, don't round that number. Next calculation should be this, but instead of me plugging in 1, what am I going to plug in? Answer, right? Okay, now, but be careful here. So this 1, instead of 1, I want answer. So it's answer minus cosine answer minus answer minus sine of the answer. Here's the catchy part. Here's the tricky part. Wasn't that just a constant 1? Do I need to change that last 1 to answer? No, that stays 1, right? That was because my derivative, let's go back here, because my derivative was negative sine x minus 1. That was just part of my derivative. It wasn't negative sine x minus x. It was negative sine x minus 1. So that's why that one's going to stay at 1. Okay? Bink. Okay, there's x3. So x3, okay. X3 is 0.739112. X4, move you out of the way. X4, exact same thing. So X4 is 0.739085. X5, because I'm still not matching up yet, right? I'm good to 3 decimal places. X5, 0.739085. .739085. And do we see how it's matching up exactly? Yes. Yeah. This is the end of the notes there, but do we see that? Yeah, you get all the way out to 6 decimal places correct. So therefore, you know, just kind of like boxed it, but you get the idea. That's where cosine x equals to x. Correct to 6 decimal places out. Yeah. 1 minus cosine 1 minus 1 divided by negative sine 1 minus 1. Oh, you're in degree mode. Yeah. These should always be in radian mode. Maybe that's some of your issues. Some of you guys are looking at me weird. If you got 0.999 something, that's degree mode. You want radian mode. What's wrong? Yeah. Yeah, you're in the wrong mode.
Well, that was the first one, but then I put it in radian.
Okay.
I'm in radian.
So recalculate that. There. Okay. Now. Yep. You gotta change that to a lot too.
Oh, that's not it.
I got the first 1.73638. So then I just do to get the next one.
Second entry.
Second
entry.
Oh, can I?
Yep. Once you have it plugged in correctly in your calculators, you just keep it in second entry, and just keep it rolling until it matches up. Yeah, there's only like 5 questions too.
Yeah.
Oh, it's your 1 out front. That should have changed to answer. Because it's always x. No, that one changed to answer. That first number changed to answer every single time. Because look here. Yeah, xn. You always have to start at xn minus fxn over f prime xn. So this number is always going to be the next iteration. Okay.
Al,